Welcome to the next video. Let's continue where we left off. So the next thing we're going to cover is called exponential graphs. Okay, so next is exponential graphs. So we have this type of exponential graph. This is 0, 1. So this is the graph of y equals a to the x, where a is greater than 1. Okay, it looks like that. The graph is concave up and increasing. Okay. Next, another graph. Okay, x-axis, y-axis. So I'm going to put the x and y-axis here. Okay. Now, this is the graph of the exponential graph if a is strictly between 0 and 1. So this is y equals a to the x if a is strictly between 0 and 1. And it's concave up also, but now it's decreasing. Okay, and so this is the exponential graph. Okay, now if you look at the way the exponential graph looks compared to a power function, you'll see how much faster it grows. So for instance, this is what y equals x squared might look like, though it's actually going to be separated to origin. So this, let's say this is y equals x squared. Okay, if I were to graph y equals 2 to the x, then our graph might look something like okay, then the graph might look something like this, though this is not. Y equals 2 to the x. So at first, y equals x squared will grow faster, will be higher. But then very quickly, y equals 2 to the x will catch up to it, and then it'll increase at a much faster rate. Okay. Okay, so now, also, if you look, let's just look at this graph, this x-axis and y-axis. This is 1 to the x. Okay. Then if I were to do 2 to the x, that looks something like this. Y equals 2 to the x. Okay, and then if you did, let's say 10 to the x, 10 to the x would be closer to the x-axis. It would come up, they'd intersect there, and then 10 to the x would increase faster at the end. So that would be y equals 10 to the x. Right? So that's the relationship between 2 to the x and 10 to the x. Now, if instead you did fraction powers, so for instance 1/2 to the x, then let's say 1/2 to the x would be a reflection about the y-axis of y equals 2 to the x. So this would be y equals 1/2 to the x. So it would be a graph kind of like this. And then if we had y equals 1/10 to the x, it would be close to the x-axis here, and then it would increase faster from going towards the left here. So you'd have y equals 1/10 the x power there. Okay, so just to give you a sense of how these graphs look. So as you increase the base, as the base gets larger here, as a number larger than 1, it'll increase faster here, and it will go close to the x-axis there. If you have a fraction, and you make that fraction larger, closer to 1, then the graph will go out like this. If you get a fraction that's very small, closer and closer to 0, it'll start hugging the y-axis here, and it'll go closer to the x-axis here. Okay, so this is pictures of exponential graphs. Okay. Okay, so the integral of a to the x dx is equal to a to the x over ln a plus c, where a does not equal y. Okay, so the most general antiderivative of a dx is a dx over ln a plus c, where a does not equal 1. Okay, so an example. The integral, definite integral from 0 to 5 of 2 to the x dx. Well, applying this formula, but now using a definite integral, we get an antiderivative of 2 to the x is 2 to the x over ln of 2. Now evaluate it from the lower limit 5 to the upper, lower limit 0 to the upper limit 5. And that's equal to 2 to the 5th over, sorry, not ln a, ln of 2 there. A is 2 here. Okay, and so it's 2 to the 5th over ln 2 minus 2 to the 0 over ln 2. And so that's equal to, that's 32 minus 1. So you get 32 minus 1 over ln 2, which is 31 over ln 2. Okay, and so that differential is equal to 31 over ln 2 using that formula. So you should know that formula also. Okay, so next is the power rule. If n is any real number and f of x equals x to the n, then f prime of x is equal to n times x to the n minus 1. Okay, so the power rule. If n is any real number and f of x equals x to the n, then f prime of x equals n times x to the n minus 1. Let y equal x to the n. Then ln of the absolute value of y is equal to ln of the absolute value of x to the n. Well, then that's equal to n times ln of the absolute value of x by the third law of logarithms, equal sign. Okay. So now, okay, so now we have that ln of y is equal to n times ln of x. So differentiating implicitly with respect to x, we get, so then the derivative with respect to x of that is 1 over y times y prime. And that's equal to derivative with respect to this, which is n times 1 over x, which is n over x. So now we have y times y prime is equal to n over x. So y prime is now equal to y times n over x. And what was y originally? It was x to the n. So this is x to the n times n over x. And that's equal to n times x to the n minus 1. So what I showed is y prime is equal to n times x to the n minus 1. Y prime is f prime of x. So f prime of x, so y prime is equal to n times x to the n minus 1. And we showed that right there, and the proof is done. Good? Okay, let's keep going. example, differentiate y equals x raised to the square root of x. Okay, so example, differentiate y equals x to the square root of x. Solution. Okay, so what we're going to do is we're going to use logarithmic differentiation, right? So before I taught you about the 3 steps to logarithmic differentiation, and so we're going to do that right here. So step 1 for logarithmic differentiation, so let me write it out, to differentiate y, we will use log differentiation, and just short for logarithmic differentiation. Okay, so step 1 is write y equals f of x. In this case, it's y equals x raised to the square root of x. That's step 1 of 3 steps, okay? Step 2 is harder. Step 2 is take the natural log of both sides and simplify this with the laws of logarithms. So then this is equal to the square root of x, ln of x, by the 3rd law of logarithms, okay? So we took the ln of both sides and we simplified this using the laws of logarithms, okay? Now we're going to differentiate implicitly with respect to x on both sides of this equation. Oh, wait. Sorry, step 1 is I consider one as step 1. Step 1 is write y equals x raised to the square root of x, take the natural log of both sides, and use the laws of logs to simplify, okay? So the end result of step 1 is that ln of y is equal to the square root of x times ln of x, okay? Step 2 is differentiate implicitly with respect to x. And so I'm going to differentiate this and this implicitly with respect to x. So the left side becomes 1 over y prime, and the right side becomes the derivative of this product. And so this is the first function in the product, that's the second function in the product. So it's the first function times the derivative of the second, plus the second function times the derivative of the first. This is x to the 1/2. And so the derivative of that is 1/2 x to the negative 1/2. Okay? So writing this as an exponent, this is x to 1/2 divided by x to the first. So this is x to the negative 1/2 plus ln of x times 1/2 x to the negative 1/2. Okay? 1 over y times y prime is equal to that. Okay? And so step 3, after we differentiate both sides implicitly with respect to x, step 3 is solve for y prime. So if 1 over y times y prime is equal to this, y prime is equal to y times that. Y times x to the negative 1/2 plus ln of x times 1/2 x to the negative 1/2. Okay, that's y. Okay, times x to the negative 1/2 x times 1/2 x to the negative 1/2. Okay, and that is the answer. That's y prime. That's differentiating y equals x to the square root of x. Y prime is equal to that. Okay, and so now we just differentiate y. That's the end of the problem. Okay, so we'll use logarithmic differentiation, step 1, 2, and 3, and that's the final answer. Okay, so, wait, so hold on, let me add more absolute value signs here. This is ln of that. This is ln of this. okay, which is now an absolute value sign goes there. Now here, you have an ln of absolute value of x here, and then there's the absolute value of x here, and the absolute value of x is here, and the absolute value of x is there. Okay, so the reason why I said because you're okay, so you take the ln of the absolute value of both sides here, and when you take the derivative of ln of absolute value of x, you then get 1 over x. I mean 1 over x here, right? When you take the derivative of that here, you get 1 over x. But then if you don't take the derivative, it stays ln of absolute value of x. Okay, that's that example. General logarithmic functions. So I'm just going to write for short general log functions. If a is positive and a is not equal 1, f of x equals a to the x is 1 to 1. Its inverse function log sub a is called the logarithmic function with base a, or the log function with base a. Thus, log base a of x equals y if and only if a to the y equals x. Okay, so this function f of x equals a to the x is 1 to 1. Its inverse function log base a is called the log function with base a, the inverse of that function. Okay, so log base a is the inverse of f of x equals a to the x for a positive and a not equal to 1. What that means is that so log base a is a function that takes the input x and maps it to y. So log base a takes as an input x and outputs y. It's the inverse of this function. And so that means, as an inverse, that means that a is the exponential function will then map y back to x. And so that means the map a to the y will map y to x. And so that means a to y equals x. Okay? So this is directly from knowing that log base a and a to the y are inverse functions of each other. Okay? Okay, so that's what we're calling log base a, the inverse function of a to the y, which exists because a to the x is 1 to 1. Okay. If and only if, again, means that this statement, this equation, has the same truth value as that statement or equation. Okay, they're either both true or both false. Okay, now if you look at the graphs of these functions, I'm going to put the graphs maybe here. X-axis, y-axis. And so if you have y equals a to the x, and then you have y equals x, then when you take this graph and you reflect it about the line y equals x, then you get that graph, that function. And now that's the graph of log base a of x, because that's the inverse graph of a to the x. I'm just reflecting that graph about y equals x. And this is for a greater than 1. Because this is y equals a to the x for a greater than 1. Okay? If a was strictly between 0 and 1, the graph looks like that. And then when you reflect it, you'll get a different graph. Okay? Okay, so one note on the side here is that you can choose any base you want. So if I choose log base e of x, then the short notation for that is ln x. So ln x is the notation for when you say that the base is e, okay? Where e is the number I mentioned before, where e is approximately 2.71828, and so forth, right? And right, and so that was the letter that I said before, that d dx of e to the x is equal to itself, e dx, right? That's the e that we're talking about here. It's also the e that says that ln of e is 1. That's how I define it, right? E was the unique real number that you could plug into ln and get a value of 1. Ln of e is 1. Okay, so log base e of x is short. Ln x represents that. And also, as another note, the cancellation equations. For log base a x and a to the x are. So these are the cancellation equations for the two functions, log base a of x and a to the x. So those cancellation equations are log base a of a to the x is equal to x, that's 1, and a raised to the log base a of x equals x. Those are two cancellation equations for these functions that are inverses of each other. Okay, so you need to know this, and you need to know that. You do need to know this too. That's important, you need to know that too. Okay, so log base a of a to the x is x, and a raised to log base a of x is equal to x. Okay, so those three things on this board you should pay special attention to. And you should know those graphs too. Okay. Okay, so we're going to erase this. Y equals log base 2 of x is that graph. Y equals log base 3 of x is that. Let's say you had a log base 5 of x. Okay, so you have y equals log base 2 of x. Looks like this. Y equals log base 3 of x looks like that. Y equals log base 5 of x kind of looks like that. So as you increase the base, the graph will start approaching, going closer to the x-axis here. And it'll kind of go like that. And then here, it'll kind of hug the y-axis more there. Okay. All right. Also, there's the change of base formula. Okay, so for any positive a, where a does not equal 1, we have that log base a of x is equal to ln of x over ln of a. That's called the change of base formula. Okay, so for any positive a that's different than 1, we have log base a of x equal to ln x over ln a. Okay, and the proof of that is this. Let y equal log base a of x. Now take the natural log of both sides, then the natural log of absolute value of Yep. Then ln of y. Then ln of y. Then ln of y is then a to the y is equal to x by definition, by the inverse of the exponential function. So if y equals log base ax, then a to the y equals x. Then ln of the absolute value of a to the y is equal to ln of the absolute value of x, taking the natural log both sides. Then, I guess I'm going to erase this. Okay, so then ln of x is equal to y times ln of a by the third rule of logarithms. And so therefore, y is equal to ln of x over ln of a. Okay, but now x and a are both positive, and so the ln of absolute value of x is ln x, and ln of absolute value of a is ln a. So we show this y is equal to ln x over ln a, and that's the proof. Okay. Okay, so that's the change of base formula and its proof. Example, evaluate log base 8 of 5 to correct the 6 decimal places. Okay, so evaluate log base 8 of 5, correct the 6 decimal places. Log base 8 of 5 is equal to, by this formula, ln of 5 over ln of 8. And in the calculator, you could take ln of 5 divided by ln of 8, and you get that's approximately 0.773976. Okay, and that's it. All done. So that example shows you the value of log base 8 of 5. Good. Good. Okay. So change of base formula, proof of the change of base formula, using it to get the answer to that example. Okay, so I'm going to erase this now. Okay, so since ln of a is constant, ddx of log base a of x is equal to ddx by the change of base formula of ln x over ln a. Because by the change of base formula, that's equal to that fraction. Well, that's the derivative, ddx, of 1 over ln of a times ln of x, right? ln of a is constant. That means that this is also constant, 1 over ln a. And so ddx of 1 over ln a times ln x is 1 over ln of a times the derivative of ln of x, which is 1 over x. So this is equal to 1 over x ln a. Okay, and so the conclusion is that ddx of that is equal to that. ddx of log base a of x is equal to 1 over x ln a. So therefore, ddx of log base a of x is equal to 1 over x ln of a. And that proves that formula. Okay, and so you should know that equation also. We'll use that space there. So as an example, let's find this derivative. So find the derivative d dx of log base 10 of 2 plus sine x. Okay, but instead of x here, it's a function of x. And so in addition to this formula, which I want you to know, I'll also say, so you need to know that one, and it's going to deduce another formula. Using the chain rule, you can show that d dx of log base a of a function of f of x is equal to 1 over f of x ln of a times f prime of x. Okay, so you also get that formula, that the derivative of log base a of f of x is equal to 1 over f of x ln of a times f prime of x. And so here, the f of x is 2 plus sine x. Okay, for this formula, I'm not going to squiggle the underline because I want to keep it without a squiggle here. Here, right now, I might squiggle the underline. This is to point out that this is the f of x in the formula. So d dx of log base 10, a is 10, log base 10 of that function, this function, is 1 over this function times ln of a, which in this case is 10, times the derivative of 2 plus sine x, times d dx of 2 plus sine x. And that's equal to 1 over 2 plus sine x times ln of 10 times the derivative of 2 plus sine x, which is cosine x. And that is the answer. That's done. So d dx of log base 10 of 2 plus sine x is 1 over 2 plus sine x times ln of 10 times cosine x. Okay, and so that example is done. So I'm going to erase all this except for this one formula for a minute, because I just want to point out a special case of this formula, which will coincide with something I already taught you. Okay, so here on this board, we found that d dx of log base a of x is equal to 1 over x ln of a, right? That's the formula I want you to know. Now, in addition, right, I taught you that, so d dx of log base e of x is equal to d dx of ln x, because, right, I told you that ln of x is at log base e of x. And so the derivative of ln x is 1 over x, right? So it's 1 over x, but by, so it's dx of ln of x, but by this formula, the derivative of log base e of x is 1 over x ln of e. Ln of e is 1, so this is 1 over x times 1, which is 1 over x. And so using this formula, we get the derivative of log base e of x is 1 over x. And that coincides with the fact we know that d dx of ln x is 1 over x, and it equals this. So this has to be 1 over x, and using this formula, we do indeed get that it's 1 over x. And so that's good. And so now we should be happy because our new formula coincides with what we previously know. Okay, there's no contradiction here. Okay, good. The number e is a limit. Okay, so remember E as a limit. So let f of x equal ln x. F prime of x is 1 over x. F prime of 1 is 1 over 1, which is 1. Now, let's compute f prime of 1 using the definition of derivatives. That equals to the limit as h approaches 0 of f of 1 plus h minus f of 1 over h, right? That's the limit of the difference quotient. That's the definition of a derivative. Well, that's equal to the limit as h approaches 0. As x approaches 0 of f of 1 plus x minus f of 1 over x. I'm just using x instead of h as the notation. Okay? That equals to the limit as x approaches 0 of ln of 1 plus x minus ln of 1 over x. Right? F of x is ln of x, and so f of 1 plus x is ln of 1 plus x. F of 1 is ln of 1. That's equal to the limit as x approaches 0. Of ln of 1 plus x minus 0 over x. And so I'm just adding this to the ln of 1 is 0, so we're subtracting that. So we get the limit as x approaches 0, that equals the limit as x approaches 0 of 1 over x ln of 1 plus x. And that's equal to the limit as x approaches 0. Using the third law of logarithms, I'm going to move this to the exponent. This is ln of 1 plus x raised to the 1 over x power. Okay, and so we know that f prime of 1 equals 1, and so we can say that limit equals 1. So now we have the limit as x approaches 0 of ln of 1 plus x to 1 over x is equal to 1. So E is equal to E raised to the first power, just like any number would be. But then this is equal to E raised to, this limit is 1, so it's E raised to the limit as x approaches 0 of ln of 1 plus x raised to 1 over x. And so now what I can do is I can move the limit outside of the exponential. So this is equal to the limit as x approaches 0 of e to the ln of 1 plus x raised to 1 over x. All right, well, e and ln cancel each other out. And so this is equal to the limit as x approaches 0 of e and the ln cancel out, and you get 1 plus x raised to 1 over x. And so e is equal to the limit as x approaches 0 of 1 plus x raised to 1 over x. So if n equals 1 over x, then n approaches infinity as x approaches 0 to the right. So e is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. Okay, so what do I mean? So if n is 1 over x, then here I'm saying the limit as x approaches 0. And in fact, x is approaching 0 to the right. And so as x approaches 0, right? As x approaches 0, 1 over n is approaching infinity. Okay? And so here, instead of 1 plus x, I can put n equals 1 over x, x also equals 1 over n. And so I can put a 1 over n there, and the 1 over x I can substitute for n. And so we get that. good. Okay, okay, so then that's E. Because the limit is n approaches infinity 1 plus over n to the nth power. Okay, good. So that's the end of 5.4. Okay, let's go to 5.5. Okay, 5.5. So exponential growth and decay. Okay, so 5.5 exponential growth and decay. Okay, so often in nature, I'll just write often, quantities grow at a rate proportional to its size. Okay, so often in nature, quantities grow at a rate proportional to its size. This means if y of t is the value of quantity y at time t, then dy dt is equal to ky, where k is a constant. Okay? So this means if y of t is the value of y at time t, so if y of t is the value of y at time t, then dy dt is equal to ky, where k is a constant. Right? That's what it means for quantities to grow at a rate proportional to its size. Dy dt is the growth rate. That's the growth rate of y. This y, I'm going to state the obvious, y is the value of y. Okay? So dy dt is the growth rate of y, and y is the value of y. So dy dt equals ky is an equation relating the growth rate of a quantity and the value of the quantity itself. And this equation is saying that that relationship is that the growth rate of this is a constant times the value of y. That's what it means for saying that a quantity grows at a rate proportional to its size. Okay? When you say that a constant a equals k times b, where k is a constant, that's what this means, is that a and b are proportional. Okay? So if a is equal to a constant times b, that means a and b are proportional. Okay? So saying that the growth rate of a quantity and the value of the quantity itself is proportional is saying that those two values, one value is equal to a constant multiple times the other value, right? So this is fairly simple, right? A equals k times b means that a and b are proportional. And so saying that the quantities grow at a rate proportional to its size means that the growth rate of a quantity is proportional to its size, meaning the value of its growth is equal to a constant times its size. The growth rate is equal to a constant times its size. That's what it means for a quantity to grow at a rate proportional to its size. The growth rate is proportional to its size, okay? Don't try and transcend the problem and try to think of something, don't try to read into the words, right? Just see that the growth rate is a constant times the size of the quantity, okay? dy dt equals k times y. If you overread or overanalyze this, you'll get confused, right? It's just the growth rate equals the constant times its size. Okay? Okay, so this is called the law of natural growth. This is called the law of natural growth if k is positive, okay? Or the law of natural decay, or the law of natural decay if k is negative. This is called the law of natural growth if k is positive, or law of natural decay if k is negative. Okay? Okay, and note, so this equation, note that the above equation that I circled, above equation, is a differential equation. Because it involves, and by involves it means it has an equation. It involves an unknown function y and its derivative. dy dt. Okay, so this is a differential equation because it involves an unknown function y and its derivative dy dt. And so that's why it's called a differential equation. That's why it is a differential equation. Okay, so I'll pause for a moment so you can copy this down. Good. Okay, so we have our equation, which is dy dt is equal to ky, right? That's our original equation, right? That says the growth rate is proportional to the size of y, right? So any exponential function y of t is equal to c e to the kt, where c is a constant. Is a solution to the above differential equation because, and so now we just have to see that it solves that differential equation. Y prime of t, which is dy dt, is equal to the derivative of c e to the kt. That's c e to the kt times the derivative of kt, which equals c e to the kt times the derivative of kt, which is k. Well, that's equal to k times c e to the kt, just rearranging the terms. C e to the kt is y, so this equals ky. And so what I just showed is that y prime of t is equal to ky. dy to t equals ky. Okay? And so we just proved that. Okay, so okay, so the solution because y prime t equals ky. If y is equal to that function, for any c, you get that equals that. Okay, y of 0, you're plugging in 0 there, you get c e to the k times 0. That's equal to c e to the 0, which is c times 1, which is c. And so what this shows is that y of 0 is equal to c. Therefore, c is the initial value of the function. Okay, the initial value of the function is y of 0. Okay, so our conclusion, which we proved already, kind of stated and then proved it, but I'm going to add a little bit more. The conclusion is that any exponential function y of t equals to c is equal to y naught, y of 0. So any exponential function y of t equals y of 0 times e to the kt is a solution to dy dt equals ky. Okay, that's the conclusion. Any exponential function y of t equals y of 0 times e to the kt is a solution to dy dt equals ky. Okay, the constant that goes here has to be the initial value of y by this argument, that line. Okay. So what we showed is that any function of this form is a solution to that differential equation. Okay, and the next theorem I write down is going to be that the only solutions of this differential equation are those functions of that form. Okay, so this statement doesn't say you found all of them. It doesn't say you found all the solutions. It just says that all of these guys are solutions. Right? It leaves open the possibility that there's another function that looks different than this that also solves the equation. But I'm going to write down a theorem that says that these are the only solutions to that differential equation. Okay? Okay. So the theorem is this. Okay, the only solutions of the differential equation dy dt is equal to ky are the exponential functions y of t is equal to y of 0 e to the kt. Okay, so the only solutions of the differential equation dy dt equals ky are the exponential functions y of t equals y of 0 e times e to the kt. Okay, so we're continuing in 5.5 exponential growth and decay. So next is population growth. Okay, let P of t be the size of the population. At time t. Then dp dt is equal to kp, or 1 over p times dp dt is equal to k. One over p dp dt times dp dt is the relative growth rate. Okay, so the name given to the quantity 1 over p times the dt is the relative growth rate. If you see 1 over p times the pt is equal to the constant k in this equation, original equation. So k is the relative growth rate in either equation. Okay, so that's the relative growth rate. Okay, so there's the relative growth rate, and here's the relative growth rate, right? So you have the relative, that's where the relative growth rate is. Okay, so saying the growth rate is proportional to its size is equivalent to saying that the relative growth rate is constant. Okay? So this equation is saying, the relative growth rate is constant. Okay, so that equation is saying the relative growth rate is a constant. Okay, so the relative growth rate is constant. And I mentioned this before, this equation is saying that the growth rate is proportional to its size. Okay, and so those two statements are equivalent. Saying that the growth rate is proportional to its size is equivalent to saying the relative growth rate is constant. Right? If the relative growth rate is constant, that means that there's a k here that equals this, and so that means there's a k that satisfies this equation, and that means the relative growth rate is proportional to its size. If the relative growth rate is proportional to its size, you can multiply both sides by 1 over p and get this equation, but that would mean the relative growth rate is constant. And so either one of these equations implies the other. And so if either equation is true, then the other equation is true. And so they're equivalent. Okay. Good. Okay. Good. dp dt is equal to 0.02p. Okay, and so what this equation says, the relative growth rate is k equals 0.02. Okay, so here t time t is in years. Okay, so this equation also says the population grows at a relative rate of 2% per year. 0.02 is 2%. So because you're multiplying the population by 0.02. That's the rate of change. Okay. So the solution P of t to this equation is P naught, which is the initial value of the population, times e to the 0.02 t. So that is the exponential function that satisfies that differential equation, right? P of t equals P of 0, or P naught, of e to the kt. The k is given by there, 0.02. Okay? Okay, and so that's our introduction to differential equations. Okay, and so next class we will go over some examples using what we learned in this lesson. Okay, so I'll see you next time. Bye.